Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Nabakis binti Muhammad Shaharuddin. Today I'm going to present design improvement and quality validation of an aircraft stowage window hook through reverse engineering and material substitution for BDX 40206 quality engineering subject. Introduction. Background of the project. The stowage window hook is critical for passenger safety in overhead language compartment. Customer supply hook showed excessive gap, poor engagement, cracking, and breakage. Original material meet 435-853 favorability requirement but failed under operational load. Project apply quality engineering principle to analyze, improve, and validate the hook. Problem statement. Replacement are challenging because hooks are outdated, broken, and unavailable from manufacturer. Existing hook deteriorating quickly under operational load, and original design and material are often unavailable. This increased maintenance need and impact safety. Although hook can be reproduced using 3D scanning and reverse engineering, a quality engineering approach is required to improve material, design, and durability. Key issues are excessive clearance, weak reliability, functional failure, lack of original design data, industrial significance, reduced operational risk, and maintenance costs ensure passenger safety. Objective of the project: select and apply new material that improve durability and performance. Implement design modification to enhance strength, reliability, and longevity. Carry out quality validation and testing to meet dimensional, functional, and safety requirements. Provide a CE-based framework for improving aircraft interior components. QE tool apply problem analysis, gap analysis, FMEA, 5-point analysis, process flow mapping, PDCA activity, material selection, design improvement, and prototype validation. Scope of the project: component focus, aircraft storage bin hook, industrial case study, PK Aviation Services Sdn Bhd. Activities include reverse engineering, material substitution, design improvement, prototyping, quality validation. QA tool apply problem analysis, gap analysis, FMEA, process flow mapping, quality validation. Literature review, main technology, and concept. Quality engineering focused on defect prevention, safety, reliability, traceability, and continuous improvement in aerospace activity. Key activity include problem identification, root cause analysis, corrective action planning, and implementation. Reverse engineering refer to rebuilding geometry, material, and function of existing aircraft interior part when original data is unavailable. Used widely for obsolete part replacement and design improvement. Literature review. Previous related research. Previous study identified obsolescence of aircraft interior part as a major driver for reverse engineering maintenance activities. 3D scanning is reported as effective for capturing complex geometry of interior plastic component. Research on elastomer materials show acceptable fire compliance but lower stiffness, fatigue resistant, and creep resistant, leading to crack indentation and deformation under repeated use. Comparative studies show flame retardant ABS provide higher strength, dimensional stability, and engagement reliability while meeting 435-853 requirement. Quality engineering case study demonstrate reduced failure rate after applying FMEA, design refinement, material upgrade, PDCA cycle, and control process flow. QE to apply problem analysis to identify root causes, gap analysis to measure performance deviation, FMEA to prioritize failure risk, process flow mapping to ensure controlled and traceable improvement, and PDCA. Problem analysis. Visual inspection identify excessive gap at the hook engagement area. Dimensional measurement confirm clearance outside functional requirement. Service records show repeated cracking and breakage during normal operation. Root cause identified as poor load distribution combined with low material toughness. Conclusion from problem analysis: Durability failure occur due to design weakness and unsuitable material that miss issue. Gap analysis. Current condition, excessive clearance cause unstable engagement and high local stress. Desired condition, control clearance with stable engagement and uniform load transfer. Material gap. Original material meet 425853 but show low wear resistant and fracture resistant. Performance gap. Short service life and frequent replacement versus target longer service life. Gap analysis outcome guide reduction of critical dimension and material upgrade. This is my table of FMEA process step input. 5Y analysis. 5Y analysis check phase. Problem storage window hook is too loose. First Y is poor fitting. Second Y is dimensional mismatch. Third Y is one old part used for scanning. Fourth Y is non-dimensional composition applied. Fifth Y quality analysis not considered during reverse injury. Root causes, lack of quality analysis and dimensional composition in early design stage. This is process flowchart for the process. Start problem identification, reverse engineering, gap analysis, FMEA, material selection, design improvement, prototype manufacturing, dimensional inspection, functional and durability testing, evaluation and documentation, and finish. For PDCA plan, related step. First step, meet customer. Second step, 3D scan and analyze data. Step 3, process selection. Activities understand production function and customer requirement, identify problem, the hook to loose, excessive gap. Perform 3D scanning on all part. Analyze dimensional wear and deformation. Select suitable manufacturing process. Output clear problem, definition and quality requirement. For PDCA, do related step. Step 4, mesh. Step 5, prototype and fitting. Activities convert scan data into mesh model, clean and optimize mesh, redesign hook using CAD file, fabricate prototype, conduct fitting test on stowage bin, output physical prototype ready for evaluation. PDCA check. Related step. Step 6. Analyze problem. Finding from fitting test. Hook is too loose. Large gap between hook and mating surface. Locking performance not consistent. Gap analysis. Aspect. Fit. Current condition loose. Expected condition firm and secure. Aspect. Gap. Current condition large. Expected condition minimal. Aspect. Locking. Current condition inconsistent. Expected condition reliable. Output perform gap clearly identified. PDCA Act. Related step. Step 7 documentation. Step 8 final product. Action taken. Adjust gap dimension and reduce gap. Improve tolerance control. Retest fitting performance. Document improvement and inspection criteria. Finalize improve the hook design. Output improve and standardize final product. Final product result. Feature. Material. Original hook. Improve hook. Feature. Material. FAR 25853. Compliant low reliability. Height strand material. DP18263. FAR 25.53. Compliant. Gap. Excessive. Reduce force stable. Reliability. Cracking and breakage. Height resistant to wear cracking. Functional reliability, low height. Maintenance frequent and reduced. QE tool effectively guide root cause analysis, material selection, and design improvement. Gap analysis and FMEA, repetition of failure. Process mapping ensure traceable and control production. Prototype demonstrate improved reliability, functional reliability, and reduced maintenance. Conclusion and recommendation. Achievement of objective, problem analyzed, material upgrade, design improve, prototype validate. QE-based framework established for improving obsolete aircraft interior component, recommendation for future ratios, extend in service testing for long-term durability, exploration of advanced material, application of QE framework to other aircraft interior component.